Let's take a look now at the idea of calculating a confidence interval for the mean. Now, extremely important concept here. Remember, a confidence interval is always, always, always used to estimate a population parameter, and it's never used to estimate a sample statistic. Estimating the sample statistic doesn't make any sense. You calculate a sample statistic, you know what it is. Okay, so there are two different scenarios that we will be looking at. The first one is when the standard deviation is known. This means when you know sigma. And the other is when you don't know the standard deviation, when you don't know sigma. Of course, you'd use S to estimate it. When you use S to estimate the true standard deviation, a few things change, so we need to address that as a separate scenario. Now, the data type applicable are both interval and ratios. This is extremely important. That's why measurement scales are important. If you're not dealing with at least interval data, you should not be here to begin with. Now, consider the following speed of light data. I'm going to use this for this analysis. From 1880 to 1882, Simon Newcomb measured the time required for light to travel from his laboratory on the Potomac River to a mirror at the base of the Washington Monument and back. The total distance was approximately 7,400 meters. The data below is Newcomb's data in units of thousands of kilometers per second. So this 280 right here represents one measurement that he took, and the estimated speed of light was 280,000 kilometers per second. That's what this data means. So just as a quick review, we know a confidence interval has a basic form of a point estimate. I'm going to say PE for point estimate, plus and minus the margin of error, ME. And from the previous chapter, we know that the sample means under the right conditions will be distributed normal. We know that X bar is distributed normal with a mean of mu and a variance of sigma squared over n. We know this from, like I said, a previous chapter. But what are the right conditions? Well, there's two. Number one, if the parent population is normal. If the parent population is normal, then I know that the samples could be normal. That's not a big deal. Or n is at least 30, so the CLT, the central limit theorem, will apply. It's one or the two here. And in this case, clearly we have more than 30, so the central limit theorem would apply. Now here, let's suppose that we know that sigma is 105. Now, granted, this is a goofy thing to say. I get it. How could we possibly know the true standard deviation for collecting data for the speed of light? It doesn't make any sense. And it's typically that way. It's very seldom that you would truly know sigma. It's kind of rare to have that. And I want to construct a 95% confidence interval. Now this interval will estimate mu, the true mean, well, the true mean time in this case. So this confidence interval is going to look like X bar plus or minus Z of alpha over 2. We've talked about the Z of alpha over 2 before. X bar is my point estimate. Sigma divided by the square root of n. That comes from here. Sigma squared over n is a variance. I want the standard deviation, so I need the square root of all this, which gives me sigma over root n. Now, we want to find the appropriate values and compute this thing by hand. So let's see. I want to find the value for X bar. I need to find the value for Z of alpha over 2. And I need sigma over root n. I know Z of alpha over 2 because it said 95% confidence interval, and I've done that previously. I know this could be 1.96. I know that sigma is 105. That was given to me right here. And then I need the square root of n, so I need to figure out what n is, and I need to figure out what X bar is. So, if I jump to TC Stats, I have this chapter 11 video data here. And there's the speed of light. So let's just take a look at the summary statistics. Whoops. I need to select it first. So I have n equals 66 and the mean of 262.121. So based on this, my 95% confidence interval should look like 262.121 plus or minus 1.96 times 105 divided by the square root of 66. Now there is an issue here. And that issue is if you look closely at the data, there's 1, 2 negative numbers. Right away we know there's a problem. You can't have negative speeds of light. That's one reason why graphs of data are so important. Here's a quick histogram, and right away looking at this thing I can see it's not exactly normal and I have negative values. This is a big thing to do. Always look at your data. If I were to instead do a quick box plot, there it is. Again, I can see I have at least one negative value here. So it's extremely important to look at your data first. So what I need to do is I need to get rid of those. So I'm just going back to TC Stat, hit edit. There's that negative value. I'm just going to erase it. And then I need to find the other one. There it is. And I will erase it. And those blanks is just simply missing data, so TC Stats is fine. So I really need to go back and do those summary statistics again and redo this with the new mean and sample size. I said new, but in reality it's the proper to 277.5 plus and minus 1.96, 105 over the square root of 64. Now with a calculator you can quickly figure out what that confidence interval is. Fortunately, we will never actually have to do this by hand. I always want to show you by hand once so you get an idea what's going on, and we can actually do the whole thing in TC Stats. So in TC Stats I'm going to select that data set, and then I'm going to go to one sample techniques, and this is a Z for the means. I'm dealing with means, and I'm using a Z confidence interval because the confidence interval is based on Z. And this stuff up here we're going to completely ignore. This is actually an upcoming chapter, but all this is combined for a good reason to make more sense in the next chapter. So I wanted a 95% confidence level, so I'm going to type in here 0.95. And then I am going to simply select this data and tell it to use the selected variable so I don't have to enter the sample mean. I do need to tell it sigma. Sigma is 105, that's what we're claiming. And then here is my confidence interval. So I have what I'm saying here is I'm 95% certain that the true speed of light is somewhere between roughly 251.77 thousand kilometers per second and 303.22 thousand kilometers per second. That is based on Newcomb's data. Now what is extremely awkward about this is using this 105 for the standard deviation, because in reality we don't know what sigma is. And because we, in reality, never really know what sigma is, we have to estimate it with S. And that's going to change some of this, which is going to lead us to the next section.